Hello, everybody. This is Mr. Festoni. Today we'll be continuing on with Chapter 2, which is about quadratic functions. And the section we'll be working on is Chapter 2.2, which is the characteristics of quadratic functions. This is actually probably the most important section of Chapter 2. And thus we'll be spending quite a bit of time on this. It's kind of a meaty chapter. So let's get down to it. So in this chapter, we have three goals. Our goals are to explore the properties of parabolas, which are, remember that parabolas are the shape that quadratic functions take when we graph them. They look like U-shaped graphs. And we're going to be talking about parabolas in vertex and standard form. So we knew vertex form already. We're going to be exploring something new called standard form. We'll be finding the maximum and minimum values of quadratic functions. And then we'll be graphing quadratic functions using intercept form, so the third form as well. We'll be starting with vertex, building into standard form, and then going to intercept form. We'll also be talking about this concept of a maximum and minimum value. So let's get right into it. So concept 1, part A, is about the vertex and the axis of symmetry, the relation between these two. We've already talked about the vertex. Remember, the vertex is just the lowest point on an upward pointing parabola or the highest point on a downward pointing parabola. If I have a parabola like this, the vertex will be at the very top, and that value or that point has the values h comma k from our vertex form, which we'll talk about in a second again. So we have this new concept called the axis of symmetry, which is a line that divides the parabola into mirror images and passes through the vertex. In other words, it basically cuts the vertex right down the middle. So this red line here is cutting down the middle of the parabola, and any point that's on one side of the parabola is effectively mirrored on the other side of the parabola, with the exception of the vertex. The vertex itself isn't mirrored because it's literally right on the axis of symmetry. It's being cut right down the middle. So the vertex of any parabola in the form f of x equals a times x minus h squared plus k, since that vertex is on the point h comma k, which we talked about right here, the axis of symmetry is the vertical line x equals h. In other terms, in other words, the line itself has the equation, the axis of symmetry has the equation. Let's say this is my line that's going to be cutting through my parabola. It has the equation x equals h. When we think about a vertical line, that means that line has the same x coordinate no matter where it's at. It could be at h comma 10 up here. Down here it could be at h comma negative 3. Every single point on that vertical line has the same exact x coordinate. And if that x coordinate is cutting right through the vertex of a parabola, that means that x coordinate is exactly the same as the h value on the parabola, which means the line is equal to x equals h, or the equation for that line is x equals h. So we're going to use this idea to reach our first goal here, which is using the concept of symmetry to graph quadratic functions. And in this case, we're going to be sketching the function. I find it's more important to understand what's happening in the picture versus graphing it perfectly. Once you understand what's going on, you can always go back and create a t-chart with your x and y values and get a very exacting picture. But I'd much rather you guys have an understanding of what is happening based on the various values in the equations. So in this function that we're graphing is -2 times x plus 3 squared plus 4. This is in vertex form to start. Actually, we're going to stay in vertex form right now. We'll be moving on to standard form in a minute. But our goals are to label the vertex and the axis of symmetry. Well, remember, the vertex is very easy if we're in vertex form. The vertex is just going to be an ordered pair in the form of h comma k. Well, in this situation, we know our k value is equal to +4. And our h value is a little bit tougher than the k value, but just remember, with vertex form, is a times x minus h squared plus k. That default of a negative sign in there is to remind us that the value is always the opposite or the inverse of the value that is in the equation. So if I've got a +3 in the equation, that means my h value is going to be a -3. And so my vertex is at -3, 4. Well, when it comes to graphing, I can put this together very quickly then. Here are my xy axes. I know that my vertex is 1, 2, 3 to the left, and 1, 2, 3, 4 up. So it's going to be a point right about there. And then I know, because of my a value, since my a value, ooh, that was a terrible a. Let's try that again. Since my a value is equal to -2, I know that I'm going to have a reflection because of the negative sign. It's going to reflect vertically. And then the 2 is going to be a stretch, also vertically. So with a -2, I know it's being flipped upside down. The u is going to be pointing down, and my graph is going to be stretched by a factor of 2. So it's going to look something like that with a vertex at -3, 4. And then it's going to have an axis of symmetry, which I'll do in this light blue color, that's going to be right at the line x equals -3. Now this is a bad sketch, so disregard this little lineup problem that I had there. Let's fix that. So I've got this blue line cutting through the parabola. Remember, it's symmetric, so everything that appears on one side is going to appear on the other. If my sketch was better, it would look more exact, but this is the concept. It's cutting right through the vertex, which means my line is the line x equals -3. And now I've covered the 2 things that I need to do, or the 3 things I need to do. I sketched the graph, I labeled the vertex, -3, 4, and I labeled the axis of symmetry, x equals -3. And I'm done. Goal 1A is complete. So let's move on to goal 1, or concept 1B, the standard form of quadratic functions, or for quadratic functions. So quadratic functions, like linear functions, can be written in different formats. The standard form of a quadratic function is f of x equals ax squared plus bx plus c, where a cannot be equal to 0. So I want to talk about that really quick. What happens if a is equal to 0? Well, if a is equal to 0, that would mean that I've got a 0 right there. I'd have 0 times x squared. Well, 0 times anything is going to be 0. So that just goes away. And what I'm left with is an equation where I've got b times a singular x, not x to the first power, not x to the second power, plus some value c. Well, if you think about this, if you replace the b with an m and the c with a b, you've got the equation for, or the right-hand side of the equation of slope-intercept form, a linear equation. So we're dealing with quadratics, not linear, so we need that x squared to get that u shape in our graph that we're looking for. So we're going to be in standard form, ax squared plus bx plus c. A cannot be equal to 0. That's really our only rule. And if we evaluate and simplify a quadratic in vertex form, it will result in standard form. So if I have something that starts off in vertex form, I can always evaluate, combine like terms, and simplify, and it will end up as standard form, which is nice. Depending on what kind of information I want to get, I can convert from one form to another. And maybe that enhances the picture of what I know already. So concept 1b, I'm converting from standard form to quadratic. Oh, I goofed up there. I'm converting to standard form from vertex form. So I'm starting off here in vertex form. A times x minus h squared plus k. I just want to show what's happening at each step. So to start off, I've got this x minus h squared. Well, just remember from our Algebra 1, if I've got x minus h squared, that's just the same as saying x minus h times x minus h. And then I can use the FOIL method. So first, outer, inner, last. First times first, x times x gives me x squared. Outer times outer, that's going to be x times negative h, that gives me negative hx. Inner, negative h times x gives me another negative hx. And then last, negative h times negative h gives me positive h squared. I can combine like terms really quickly. I end up getting x squared minus 2hx, because there are two of them up here, 1, 2, plus h squared. Now this little expression here gets substituted in right there at step 2. So I've done my FOIL method and I've expanded that out. My next step is I'm taking this a value and I'm multiplying it by all 3 of the values in this parentheses, which leads me to a situation where I'm distributing, and I get a times x squared gives me ax squared. A times negative 2hx gives me negative 2ahx. And then a times h squared gives me ah squared plus k. So I'm almost done. Remember, from vertex form, the a value, the h value, and the k value are all numbers. They're not variables. They are numbers for our specific equation. X is a variable that we input, but a, h, and k in any given equation typically have values. A might be 3, h might be negative 8, k might be 12, whatever. But they are all numbers. And since they're all numbers, we can do some nice things. For instance, well, a, there's nothing special about. A stays with a, so ax squared becomes ax squared. But for b and c, we get some interesting stuff. Negative 2 times a times h, a number times a number times a number, will equal another number. So I'm going to substitute negative 2ah with the value b. And then same with a times h squared plus k. A is a value, h squared is a value. You multiply those together, you still have a number. Add k to it, that's another number. So I have c. So I get this nice equivalency where a is a, b is equal to negative 2ah, and c is equal to a times h squared plus k. So really quickly, just a little side note here, we'll explore this more in a second, but if I've got b equals negative 2ah, well, remember, on vertex form, the axis of symmetry is x equals h. So if I can solve for h, I can figure out my axis of symmetry. So if I'm in standard form, I can find my axis of symmetry just by dividing both sides of the equation by negative 2a. What that ends up doing is eliminating the negative 2a on the right side, and I get b over negative 2a equals h. But we know that h is also equal to x, So it's also equal to x, which means my axis of symmetry can be expressed as the equation x equals b over negative 2a. In other words, I eliminated that middleman. Since this is equal to this is equal to this, I can get rid of the middle guy, and I know that x is going to be equal to b over negative 2a. So we'll be using this equation to find our axis of symmetry when we're in standard form. Also, with our c value, we get some interesting stuff going on too. So with c, we know c is equal to h squared plus k. But if you think about vertex form, we know that vertex form looks like this. Well, what happens if I plug a 0 in for x? If I plug a 0 in for x, I get the following. A times 0 minus h squared plus k. If I continue along that train of thought, I get a times negative h squared plus k. Well, negative h times negative h is going to be positive h squared plus k. Well, what do we know? That's the same thing that we had up here, which means that the function at 0 is equal to this, which is equal to my c value, which means when my x value is 0, my y value is c. But more importantly, remember, if the x value is 0, if you think about a graph of any value, if my x value is 0, that means I'm somewhere right along the x-intercept. All of these values, no matter where I put a point along here, my x value is 0. Oops. My x value is 0. Maybe I've got a negative 3 down here. Up here, I've got a 0 and maybe a positive 4. But for the purposes of this vertex form equation or standard form equation, if f of 0 equals c, that means that when x is equal to 0 on whatever parabola I have, my y value is equal to c, which in other words means that my c value here is going to be my y-intercept. So for any quadratic function in standard form, this c value right here represents the y-intercept. Didn't turn off my arrow thing. Y-intercept. The b value in conjunction with the a value I can build the equation for my axis of symmetry. X equals negative b over 2a. I plug in both the b and the a and I can find my axis of symmetry. So I get a few things right from the standard format. I get my axis of symmetry if I do a little bit of math with b and 2a, and I get my y-intercept just by looking at that c value. So let's see how this works with a real equation. Oh, I still have another screen. This is just additional stuff that's just explaining what's going on. So again, if I think about my equations, my axis of symmetry, which I'm going to just refer to as the AOS, is this equation right here. And then my y-intercept is the value c. If my a value is bigger than 0, my parabola is going to point up, which we can see here. And if my a value is less than 0, my parabola is going to point down, which I can see here. All right, let's continue along. So goal 1, part B. Again, we're going to be sketching the function f of x equals 3x squared minus 6x plus 1. And what we want to do is we want to label the vertex and the axis of symmetry. All right, so first off, what I want to do is I want to identify my a value, my b value, and my c value, just to start off. So I've got those laid out. My a value is equal to 3. My b value is equal to -6. And my c value is +1. So based off of that information, I can get a lot very quickly. So remember, I can find my axis of symmetry just by combining my a and b value in an equation. So my axis of symmetry is -b over 2a. Well, negative sign, my b value is -6. 2a is 2 times 3. Do some math. I've got a negative of a negative. Those become positives. So, or evaluating everything, I get a +6 up top. 2 times 3 also gives me a 6 on the bottom. 6 over 6 gives me +1. So my axis of symmetry is at +1. Or in other words, the line x equals 1. So I've got my axis of symmetry figured out. I still need my vertex. Well, I'm not in vertex form, so I can't really determine what my vertex is by looking at the equation. But what I can do, go over here, and do a quick graph. And again, this is a sketch. I know that my axis of symmetry is going to be right at the line x equals 1. So I'm just going to put a dashed line here. This is my axis of symmetry. It's going to cut through this parabola, wherever the parabola is. It could be a parabola that looks like this. It could be a parabola that looks like that. It could be a very wide parabola. I'm not exactly sure, but I know it's going to be cut right down the middle by this line, x equals +1. Well, what I can do, because remember, I've got this equation, 3x squared minus 6x plus 1. Well, what happens if I've got, let's do this in white, 3x squared minus 6x plus 1. If I substitute a value for x in, for instance, if I substitute a 1 in for x, what I end up getting is the following. 3 times, let's do it like this. I'll put all the spaces where my x's will be. Now I'm going to fill in the x values with 1. Oh, and I've got a square right there. So f of 1 is going to be 3 times 1 squared minus 6 times 1 plus 1. Well, 1 squared is just 1. And 3 times 1 is going to be 3. Negative 6 times 1 is going to be -6. And plus 1 is still plus 1. Now we're just combining like terms. 3 minus 6 is -3. Plus 1 is -2. So when my x value is 1, my y value is 2. Or if I were to plot this, I would plot the point 1, comma, -2. But think about that. If my x value is 1, that means I'm on the axis of symmetry. If I'm on the axis of symmetry and I'm a parabola, that means that that point that's right on the axis of symmetry is gonna be the vertex. So I now know that my vertex is at 1, comma, -2. And there we go. Now I've got my vertex. Last thing I need to do is graph it. So I could still try to graph using an XY table, but remember I've got another value in here. I've got this C value of +1. If my C value is equal to 1, that means that my y-intercept is right at the value 0, comma 1. And think about that again. If I've got 3x squared minus 6x plus 1. If I plug a 0 in for x, this becomes 0, that becomes 0. The only thing I'm left with is a 1. So if I plug a 0 in, my y value is going to be +1. So there's my y-intercept right there at 0, comma 1. Well, because I've got that, remember, a parabola cuts everything right down the middle. Well, if it cuts everything right down the middle, it means I'm going to have a curve that goes down to there. Well, if the distance from the y-intercept to the axis of symmetry here is 1, I can mirror that in the other direction by 1 as well. Let's try that again. So I'll have a second point. Every point on a parabola is mirrored over the axis of symmetry, with the exception of the vertex. That means the point 2, comma 1 is also on my parabola, and that my parabola looks something like that. Again, this is a bad drawing, especially this left side. Let's see if I can fix that. It's a sketch of what's going on. And what I get is a parabola that has a vertex at 1, comma -2, a y-intercept at 0, comma 1, a mirrored point for the y-intercept over at 2, comma 1. And with those 3 points, I can do a rough sketch of my parabola. Because with any 3 points, you've got the vertex, a point, and then a mirrored image of the second point, I can create that U-shaped graph. Vertex, some random point, mirror image, sketch of the graph. So now I've got the sketch, I've got the axis of symmetry and the vertex labeled. I'm done. I've got everything I need. All right, let's continue. Almost done with, oh, actually we are done with goal 1. Let's knock out goal part 2. So goal 2 is a new concept. It's called the minimum and maximum values, or the maximum and minimum values, because I apparently like to reverse things when I'm recording videos. So the maximum and minimum values. So since the vertex is always the highest or lowest point on a parabola, that depends on the direction it's pointing. If it's pointed up, it'll be the lowest point. Think about like the lowest point in a valley. Or if the parabola is pointed down, it looks like a mountain, and the vertex will be the top point on that mountain. The value of that y-coordinate for the vertex is considered either the maximum or the minimum value of the function. In other words, if I've got a parabola that's pointed up, like right here, that vertex is considered the minimum because it's the lowest value, and that minimum value is described as whatever the y-coordinate is. So if this was at, I don't know, 2, 3, that would mean that the minimum would be 3, the y value of that point. Likewise, if I've got a parabola that's pointed down, the maximum value is that of the vertex. It's at the very top of the mountain. And again, if I've got some value for this vertex, let's say let's say it is at 2, 5, that maximum value will be the y coordinate of the vertex, or in this case, a value of 5. The highest point on the graph is 5. So with that, we can very quickly find minimum or maximum values. So let's find the minimum value or the maximum value of the following quadratic in standard form. And this quadratic is f of x equals 1/2 x squared minus 2x minus 1. So it's in standard form. Let's keep track of all the different values that we have here. I've got an a value of 1/2. I've got a b value of -2, and I've got a c value of -1. So with these three values, I can put together my image of this graph and figure out what's going on here. So I need to figure out if it's going to be minimum or maximum. But what I can do with that, how I can figure that out easily, is just by looking at the a value. My a value is 1/2. That means I've got a positive a value, which means my graph is going to be pointed upwards. Since it's 1/2, it's actually going to probably look a little bit like this because it's going to be vertically shrunk. So I know it's going to be a minimum value that we're going to have because my vertex is going to be at the very bottom of this graph. So let's go ahead and figure out the rest of what's going on. With my a and b value, I can find the axis of symmetry very quickly. Remember, that's just the line x equals negative b, which in this case, my b value is -2, over 2 times a. In this case, my a value is 1/2. So I've got -2 over 2 times 1/2. Let's go ahead and evaluate that. A negative times a negative becomes a positive, so I have +2 over 2 times 1/2 gives me 1, which means my axis of symmetry is on the line x equals 2. And then lastly, my c value tells me where my y-intercept is. So I've already got some information about my graph. I know it's pointed up because my a value is positive. I know my axis of symmetry is at 2, and I know I've got a y-intercept at -1. So I could graph that very easily. In this case, though, what I really need to do is determine my vertex. So remember, my x value is equal to 2. I've got the graph. I'm just going to write this right here. Sorry, not the graph. I've got the function. Probably shouldn't be recording these at 11:15 at night, but, you know, lesson learned. So if my x value is 2, I can plug a 2 in to my equation wherever the x was. So 1/2 x squared minus 2x minus 1. I plug in a 2 everywhere x is at. So my function at 2 looks like this. I can evaluate. 2 squared equals 4, so I have 1/2 times 4 minus 2 times 2 is also 4, minus 1. 1/2 times 4 is 2. 2 minus 4 gives me -2. Minus 1 gives me -3. So in other words, when my function is at the x value for 2, or f of 2, my y value or my output value is -3. So my function value at 2 gives me a -3. That means if I were to sketch this, my axis of symmetry is over here at +2, 1, 2. There's my axis of symmetry, cutting right through 2. And if I plug in a 2 into my function, my output gives me a -3, -1, -2, -3. So my vertex is going to be down here at +2, -3. I also know that my y-intercept is right at -1, which means the left side of my graph is going to look something like that. And then the right side of my graph will also go up here with a reflected point of this y-intercept over here on the right at the point 4, -1, because this over here is 0, -1. I've got a space of 2, a distance of 2 to the axis of symmetry, which means I've got a reflection that's also 2 away from the axis of symmetry on the other side. Start at 0, go over 2, axis of symmetry, go from 2 more to the right, gives me 4 for the other point for the x value. This is a little bit of extra stuff that I'm doing just to build the picture. These things aren't actually needed. Right now, we're just trying to determine the minimum value of this graph. Well, the minimum value is going to be the y value of my vertex. If my vertex is at 2, -3, that means that the minimum value is -3. Or in other words, the lowest value on my graph is -3. If you think about this green graph, can't erase things apparently. This green graph of this parabola, the lowest point is right at -3, my minimum. All right, so that's the first part. We wanted to find the minimum value or the maximum value. There was not a maximum value because it was a parabola that's pointed up, but we found the minimum value, and that's at y equals -3, right at the vertex of the graph. Now, we also want to describe the domain and range of the function and where the function is increasing or decreasing. I didn't talk about this, but if we go back up to this chart, you can think about a quadratic kind of like a roller coaster. I'm going downhill until I reach the very bottom of this hill. For a split second, I'm neither going uphill or downhill. I'm decreasing until I reach this point. And then after I pass that point, I start increasing. So for every upward pointing parabola, as you're coming from the left to the right, and remember, we always read graphs from the left to the right. As you're coming from the left to the right, you're decreasing, decreasing, decreasing until you hit that minimum value, and then you start increasing again. Similarly, with parabolas that are pointed downwards, it's like going up a hill in a car or on a roller coaster. You're increasing, increasing, increasing until you reach that maximum value, which is your vertex. After that, you start decreasing as you continue to the right. And again, you read graphs as if you're going from the left to the right, just like a book. All right. So if I want to describe the domain and the range of the function and where the function is increasing and decreasing, I can talk about this in very simple terms. I'm going to erase some of the stuff that's going on just to clear things up. So I am decreasing as my x value comes from the left, way out here at -infinity. as my x value goes from negative infinity to positive 2, I am decreasing. After I hit positive 2 and continuing on forever as I go towards positive infinity, my graph is increasing. And then the domain and the range, we didn't talk about this very much, but the domain is just where all the x values can be. For this function, my domain can be any values. I can plug any value I want. I can go as negative as I want, plug that value in, run it through the equation, and I'll get an output value. So my domain goes all the way from negative infinity to positive infinity. My range, on the other hand, these are the y values. I do have a lowest value. I have a minimum at negative 3. So the lowest value I have is negative 3, but then as I increase upwards, this graph goes on forever in an upward direction on both sides. So while there is a lowest value of negative 3, there actually is no maximum value. So my domain goes from negative infinity to positive infinity. My range goes from negative 3 to infinity. And that's it for goal number 2. I'm going to stop this video right here. We're going to finish the video for concept 3, which is intercept form, in the next video. Like I mentioned, 2.2 is very long. Intercept form is not too bad. Actually, it's only a couple slides. Maybe I'll just do it. All right, let's finish this out. Concept 3, graphing quadratics using intercept form. I apologize for getting your hopes up. Let's finish this out. For graphing quadratics using intercept form, we have a third format, intercept form. In fact, actually, I am going to stop this video here. This will be a micro lesson. I'll do this next. Apologize. Let's stop recording.